All right, our next subject is going to be reflection and reflection. Reflection and refraction. We learned that diffraction was when light hits a barrier, it can bend around behind it. Reflection is when light or any wave bounces off a surface. And it's really straightforward. Here's my surface. All right, I got my wave coming in this way. We're going to call that the incident ray. And when it hits, it's going to reflect off this way like a billiard ball. It just hits and bounces off like that. This is the reflected ray. And this angle are going to be the same. The only thing that's a little confusing is we don't measure the angles from there, from the surface. We draw in what's called a normal line. And just like a normal force perpendicular surface, the normal line is going to be a perpendicular surface. I draw it in dash because it's not really there. It's just something I'm using for a reference. And I'm going to label this theta I and theta R. Theta I stands for incident angle. And theta R is reflected angle. And the law of reflection is just that theta I equals theta R. That's very simple. Now, refraction is when light changes, when light or any wave changes material and bends. Okay, and you've probably seen this if you have a glass of water and there's a straw in there, and you look at the surface of the water, the straw looks bent. It's not that the straw is bending, it's that the light that's coming from the straw, when it hits that surface of the water and goes into the air, it bends. Why this occurs? When light changes speed, it bends. And you might think to yourself, well, wait a minute. Light is always going 3 times 10 to the 8th, or it has been in every problem we've done so far. And I didn't mention it, but that's the speed of light in a vacuum. So that's its speed when it's in a vacuum. But it's going to be different in any other material. So now we're going to have a diagram that explains this. And this diagram is a little bit tricky to draw. So just do the best you can and try and follow along. Here's my surface. We're going to say up here we have air. And light in air is very fast. And down here we're going to have water. And in water, the light is slower. All right? And I'm going to draw the waves like waves crashing into a beach, but at an angle. So in the air, I'm going to have it going like this. And try to make these nice and parallel, just like the crest of the waves going into the beach. They're going to be nice and parallel. So these things are coming into the beach like this. Okay, that's the direction they're moving. So my light ray is coming down here like this. Now, because the light is slower, the waves are going to lag behind when they get in the water. So instead of this line being extended straight this way, it's going to end up getting behind a little bit, so like that. And again, try to draw these in nice and parallel to each other. Oops. like so. And now we can see that instead of going this way, now the light is kind of going down this way. So like that. So it is bent because it slowed down. Now, before we can measure any angles, we have to draw in that normal line. So there's our normal line. And we can label this theta 1 and this theta 2. And we're always going to find that when it goes from fast to slow, the angle gets smaller. So where light is faster, we have v is bigger, its velocity is bigger, right? That's what faster means. The angle is going to be bigger, right? The angle here where it's faster is bigger than the angle here where it's slower. Remember, measuring from the normal line. And we can tell one other thing too. The crest to crest distance is a wavelength. So this is the wavelength in the air, and this is the wavelength in the water. So the wavelength is bigger. And the one thing that we need to know is that the frequency stays the same when changing materials. Okay? Now, index of refraction. And the letter for the index of refraction is N. N is a measure of the speed of light in a material. The equation for N is N equals C over V, where C is the speed of light in a vacuum. And V is the speed of light in the material. So our value for C is going to be 3 times 10 to the 8th. And they use the letter C because it's constant. It's always the same number. Now, N for a vacuum is just going to be 3 times 10 to the 8th divided by the speed in that material that's still a vacuum, 3 times 10 to the 8th. So 3 times 10 to the 8th divided by 3 times 10 to the 8th is going to give me 1. And that's an N for air. Air is pretty thin. It's going to be almost the same as a vacuum. So that's going to be about 1 as well. And that's one you should know. N for any other material is going to be greater than 1 because I'm going to do the speed of light in the vacuum divided by the speed of the light in the material is going to be smaller because it's going to be slower than it is in the vacuum. So you have a bigger number divided by a little number, that's always going to be bigger than 1. And big N is equal to a slow material. So up here where light is faster, we can add that N is going to be smaller. Smallest N is 1, that's for a vacuum, that's where it's fastest. Okay, and the bigger the N is, the slower the material is going to be. There's one more equation I'm going to give you that we're not going to use in this set of notes, but we will be using it at some point. And it's going to be N2 over N1 equals V1 over V2 is lambda 1 over lambda 2. You notice there's kind of a reciprocal thing going on here. Okay, when N is big, V is small, so they're opposites. So this is N2 over N1, but then it flips, is V1 over V2. Now a little bit more math that goes with this is something called Snell's law. And it's going to relate our index of refractions to the angles in the materials. And it's going to be N1 sine theta 1 is N2 sine theta 2. So the index of refraction for the first material times the sine of the angle in that material is going to equal the index of refraction of the second material times the sine of the angle in the second material. So here's an example. I have water up here with an N of 1.33, and I have some sort of glass down here with an N of 1.5, and my ray is coming in at a 35-degree angle. And we're going to use this equation to figure out what the angle down here is. But before we even do that, we can do the second part, the sketch in the reflected and the refracted ray. Well, here's my surface. The light's going to come down here, and some of it is going to reflect and bounce out that way. So here's my surface. It's going to hit that and bounce off. And I know that that angle is going to be 35 degrees because the incident angle and the reflected angle are always the same. I'm going to call this theta 1, and I'm trying to find theta 2 down here. But I can actually sketch it before I even figure out the amount, because this N is 1.33. This is going to be the faster of the two materials because it's smaller N. And then this is going to be the slower material. And what we found out in the last one is where it's faster, the angle is bigger. Where it's slower, the angle is smaller. So I know that the angle over here is going to be less than 35. So I'm trying to draw it a little bit skinnier than that 35-degree angle. I'll make it more obvious. Okay, it should be less than that guy, theta 2. And that's what we're trying to find. So N1 sine theta 1 is N2 sine theta 2. So 1 is water, that's my first material. So 1.33 sine of the angle in the water was 35 equals 1.5 sine theta 2. Now I just need to solve. So 1.33 times the sine of 35 gives me 0.763 is 1.5 sine theta 2. Divide both sides by 1.5. And that's going to give me 0.509. Then I'll take the inverse sine, and I will get that theta 2 is equal to 30.6 degrees. So that was quite a bit. Reflection is easy. Refraction, you have to be able to find the index of refraction and use Snell's law to find angles.